Okay, we're looking at problem 314 in the book. Here we have a pirate swinging on a rope. So going from, that's like a pendulum basically he is, going from one side to the other. It says that he passes the ground once every 1.2 seconds. So we're talking about going from here up and then back to here. In 1.2 seconds. That is a half a cycle. So our period is half a cycle, 1.2 seconds per half a cycle, which means that the period is 2.4 seconds per cycle. Be very careful that you're counting the number of cycles correctly. So that's the period of the oscillation. How long will it take him to swing 14 cycles? Well, the period we know is 2.4 seconds per cycle, which is delta t per number of cycles, and we want to know how long it will take for 14 cycles, so the period will be the same. So I can just solve the expression for that delta t. So 2.4 times 14, the units check out there, the cycles in the numerator cancel the cycles in the denominator, gives us 33.6 seconds. And what could he do to increase the frequency of that oscillation? So if the frequency is up, that means the period is down. It takes less time for one cycle to happen. So how can we make the pirate take less time? It's not dependent upon his mass, it's not dependent upon the amplitude. All he could do is climb further up the rope so that the rope is shorter in essence. That would shorten the period and thereby increase the frequency of the oscillation. Okay, here's 315. It's a simple application of the definition of frequency. You're given that the frequency of this tuning fork is 440 Hertz. Well, that's got to be the same as the frequency of any other of any time interval. So we're looking for 650 cycles in some time delta t. So I can solve. I'm going to multiply delta t up and then divide the 440 Hertz under. And I'm going to, at this point, substitute for Hertz cycle per second so that I can check the units. The cycles cancel, and the seconds is in the denominator of the denominator, so it goes up to the numerator. So 650 cycles is going to take just over a second. It's going to be 1.48 seconds. Okay, we're going to look at problem 18 in the book. Again, an application of the definition of period. We know that the period of this of the car's oscillation is 0.8 seconds per cycle. That's the same as for any other number of oscillations. So we know it takes 6 seconds for some number n of oscillations. We're just trying to figure out what n is. So I'm going to multiply n to both sides and divide the 0.8 seconds per cycle under. Check my units, seconds cancel, cycles, denominator to the denominator, so it goes up. So we're going to get 7.5 cycles that it's going to go through.